Good afternoon. Let's continue with our discussion about source resistances. So last last few lectures, we've talked about sources, voltage sources, current sources, and how a real life source will have some resistance, and that source resistance will absorb some of the energy. And so any design of a power source needs to take into account the internal source resistance. Okay. So let's look at an example of a standard battery cell. Okay. And see if we can. All right, there we go. All right, so standard batteries, no matter what electrochemical chemistry they have, whether it's alkaline, nickel cadmium, nickel metal hydride, lithium ion, lithium polymer, or even the lead acid batteries, the acid batteries that we have in our vehicles. All of those batteries have a resistance. Okay. In simple terms, we can also state that the electrochemical reactions that take place will have a finite rate. Okay. So the batteries have some electrochemical or have some chemicals inside, and the chemical reactions that occur in there have a finite rate, and that could result in a resistance. All right. So if you take a standard battery, let's say like a AA battery, and we wish to measure the source resistance, what we can do is we can model the battery as a voltage source in series with a resistor, which is Rs. The value of the battery is rated at 1.5 volts. Rs is unknown. And what we can do is we can put a current sink at its output terminals. Okay. And the current is going to send a known quantity through our battery. Okay. It's going to send a known quantity through our battery. Call it I test. So this first graph here shows us the input that we are applying as a function of time. And then here is the output voltage that is measured at that corresponding points in time. Okay. So we are applying what is known as a step input. You can see steps up, steps down. So it's known as a step input. The step input, we have two levels. We first apply a small current I1 and then step up to I2. Okay, step up to I2. And then we measure the voltage that is available at the output terminals. Remember, we cannot probe inside this. This is sealed, right? It's internal. That means we cannot probe inside that battery itself. Now, like Ohm's law and KVL, combination of Ohm's law and KVL gives us the equation that the output voltage is the source voltage Vs minus the voltage drop across that source resistance, right? Source resistance is Rs, unknown to us. We know the current that's going to flow through that battery cell. So once we have that, and we know Vs is set for 1.5 volts, so 1.5 volts minus that voltage drop should give us that KVL, should be the result of that KVL expression. And so we measure first the voltage for a response to I1. Next, we step up the current. If we step up the current, then it's pulling more current from the battery. Then the voltage drop across that resistor increases. Since the voltage drop, voltage drop across the resistor increases. And since that voltage drop increases, then the output voltage should decrease. Okay. So the output voltage will decrease. And so there is a step down in the output voltage. So there's a drop in the output voltage. Does that make sense to everyone? If you have a battery, we have a current like Ohm's law, like KVL, and then Ohm's law, and we can measure the output voltage or the change in the output voltage as a result of change in the current. Then we apply Ohm's law again, and that gives us Rs is equal to delta V over delta I, the change in the voltage or the change in the current. Again, from Ohm's law, V equals IR. Okay. Let's take a pause. Let me know if you have any questions. Does the process make sense? Okay. So as the batteries get older, the output voltage keeps dropping. And several reasons for that. One is this. Also, if you're going to put too much of a load at the output, then the voltage will drop because it's going to cause more of a drop inside the battery, thus causing less voltage to appear at the output terminals. As a real life example, if you go to this link, you should be able to find data on the internal resistance of a standard alkaline battery. It's a finite number, but it's very, very small, right? It's typically less than 0.2 or 0.3 ohms. So for a Energizer alkaline battery, it's about 150 to 300 milliohms, meaning it's 0.15 to 0.3 ohms. Very, very small. Okay, but it's present nonetheless. Not an ideal source. An ideal source doesn't have resistance, but no such source exists in real life. And on the next page, we have an example for student practice. Well, the answer is already given, so you can calculate. And check out this battery. Shows a graph showing that the change in voltage drop is 1.485 to 1.378 if you apply a 0.5 amp step change. So the RS for that would be simply change in voltage, delta V over delta I, comes out to be 0.214 amps, 0.214. Okay. And then as exercise, I would assign this for student practice. Okay, this should enhance your understanding of that topic. Right. Okay. So then let's get to the important topic of Thevenin and Norton. Oops. All right. Just a bit of background. How many of you, before I begin, how many of you have heard of Thevenin and Norton? It's something that's, I think it's this week's lab. Okay. E-students also don't study this until like the end of their circuits one class, so probably close to the end of the quarter. Leon Charles Thevenin was a French telegraph engineer in the late 1800s, like 1880 to 1890. He postulated a theory, and his theory was that if you have a large linear circuit comprised of linear sources and linear elements and linear components, you could represent the entire circuit containing multiple sources and multiple resistors. You could describe the entire circuit with only one voltage source. I could describe it as one voltage source. Okay. And of course, that voltage source would have a resistor in series. So you have a large linear network comprising of multiple sources, multiple resistors, could be hundreds of them, thousands of them, millions of them. As long as it's comprised of linear elements, you could represent that entire circuit as one single voltage source in series with a resistance. That theorem came to be known as Thevenin's theorem. It's a very important concept in circuit analysis. It's a very useful concept when you're trying to reduce circuits. Also, when you're trying to create like a sealed box, okay, like a sealed box representation of a larger circuit. For instance, we have these benchtop supplies and instruments, right, on the lab bench. We can represent the entire circuitry inside as simply one single voltage source in series with a resistance between its output terminals. So between two terminals, positive, negative, you have a resistor in series with a voltage source. That voltage source is known as the Thevenin voltage. The resistance is known as the Thevenin resistance. Okay. And so, as I said, it's a voltage source in series with a resistor. This is known by various names: VT, VTH, RT, or RTH. I prefer to use TH just so it clarifies that it's Thevenin. And of course, these are the two output terminals. And then few decades later, there was an engineer working in Bell Labs, working on a lot of audio equipment and a lot of audio circuits. And he postulated his own theory based on Thevenin's theorem, stating that you could take this entire circuit and represent it as a single current source. And of course, the current source has a resistor in parallel. And so his theorem, which came to be known as Norton's theorem, comprises of a current source in parallel with a resistor. And so this is Thevenin. And this is Norton. The output pair of terminals remain the same. They do not change. This resistance also does not change. It is still the Thevenin resistance. This current is noted as IN. The Thevenin theorem and Norton's theorem. These are the two most important ones. And then let's look at why, how and why we would do this. Okay. Okay. All right. So let's say we have a system, electrical system comprised of numerous sources. We have numerous passive components in there: resistors, capacitors, resistors, not inductors and capacitors. And then we want to take all of these resistors and represent by its one single REQ value. Okay. So between the pair of terminals right here, I'll call these terminals of analysis, terminals of interest, terminals of analysis, anything works. Output terminals will be referred to by a multitude of names. Okay. So here we have sources, voltage source, current source, and the circuit also is comprised of multiple resistors. So if you want to reduce this, we can solve for the circuit if we know that the circuit only has one single REQ. It simplifies our analysis techniques, right? So if you're tasked to find any of these quantities, whether it's voltage or current or power, between any two such systems, we can use the equivalent circuits, Thevenin circuit or the Norton circuit, and we can simplify our analysis. So with the Thevenin equivalent, we have a voltage source in series with the resistance, VTH, RTH. With a Norton equivalent, it is Norton current, and says Norton resistance, but it is the same Thevenin resistance. Okay, there's no difference. One other thing is, and we will look at this in detail. Why is it? Okay. One other thing I always like to point out even before we begin discussing is this. We have a large circuit, right? And we say that the large circuit is equal to our Thevenin equivalent network. So we are saying A, which is a large circuit, is equal to X. And then we also say that A could be equal to Y, which is our Norton equivalent. So what can we say about X and Y? Exactly. So if the Thevenin equivalent, sorry, if this circuit is a Thevenin equivalent to a larger circuit, and this bottom one is a Norton equivalent to a larger circuit of the exact same circuit, then we can say the Thevenin and Norton circuits are equivalent to each other. And from that conclusion, we can state, we can transform a voltage source into a current source if it suits our purposes. And that technique is known as source transformation. Known as source transformation. Source transformation sometimes can be tricky. I typically do not like to use it often in my circuit analysis because we have to break away the sources from its two nodes and then transform it and then plug it back into the circuit. Okay. So after this introduction, let's look at a couple of examples. So we have two voltage sources connected in series. We have two voltage sources connected in series. We can simply sum them up especially if they're connected back to back with positive, negative, positive, negative. And then we can say that the total voltage appearing at the outer two terminals is simply a sum of those two voltages. Okay, so in general, VTH is simply a sum of all the voltage sources in that series connection. Is this always the case though? Let's say you have two batteries. Like in a remote control or a RC vehicle, you might have inserted batteries in there, and those batteries are connected in series. Perhaps a flashlight. Nowadays, even flashlights come with built-in batteries. They might not have done that. But has anyone ever done that? Put in batteries into a remote? And have you ever noticed there's a metal strip at the outer end, at the back end? And then the batteries are connected one facing opposite directions. And what we are doing is we're connecting them in series. So when they're connected in series, you have two 1.5 volt batteries. The total voltage at the outer two ends is 3 volts. And that's the purpose. I have a remote control for a like 15-year-old device that takes 3 batteries. So it's 3 batteries in series. The total voltage would be 4.5 volts. 20 years ago, I had a RC truck, like a toy, RC toy truck, that took like a battery pack with 8 different cells. So 8 times 1.5, because those motors require a lot of power. And so the total voltage out of that battery pack, well, depending on the connection, obviously, if it's just 4 connected in series and then 4 in series in parallel with another 4 in series, output voltage would be 6 volts. Okay, otherwise 12. So depending on how many batteries or how many sources you have connected together in series, you can simply add up the voltages. The reason we can do that is if we apply KVL, let's say you have a battery here, you have a battery here, and you have a battery here, and you're trying to measure the voltage V out. This is 1.5 volts, and this is 1.5 volts connected in series, and you apply KVL, V out is equal to 1.5 plus 1.5. So V out is 3 volts. Right? However, what would happen if you connect them like this? What is V out in this case? Anyone? Let's take a pause while you write that down. Think over that and let me know the answer or your questions. What do y'all think? What is V out? 0. So even though technically we could say that these are connected in series, because only 2 components coming together at one point, right? So the physical connection in series, but the electrical connection would not result in a voltage. It'd just be 0 volts. If the 2 voltages were different, then yes, you would have an output. But if you have like 2 similar voltages, 2 values, then the output would simply be 0 volts. Something to keep in mind. Yes. So question being asked is if there were 3, perhaps one more here or here. Yeah, you'd simply apply KVL to find the value. Yeah, answer would be 1.5 volts. If it was connected, let's say, since we are talking about it, let me just answer it anyway. If this was like this, and I had minus plus, V out is 1.5 volts. If so, it's connected minus, the other way around, meaning plus and minus, then V out would be minus 1.5 volts. Because plus would be here, minus would be here. Yes. Which one? This one? They have pluses on the end. No. The total resulting voltage would just give us V out 1.5 volts with this polarity. The plus and minus of the voltage source or of any component simply indicates which end of that component is at a higher potential. So if you have a voltage source with a plus and a minus, then the plus terminal is higher than the negative terminal in electrical potential by its rated value, which in this case would be 1.5 volts. That's all it means. It doesn't mean anything else. Okay. So that's VTH. Here's coming back to the main point. The main point is if you have series connected ideal voltage sources, we can stack them in any order we want. We simply add them all up by applying KVL, and that's our total Thevenin voltage. That's our V out. That's the total Thevenin voltage. Okay. So that's the total equivalent value. Now, of course, that would be very convenient, right? If everything's connected in series, we could simply just, do a simple mathematical calculation and obtain our answers. However, sometimes those are not, that's not such, that's not the case. And we look at that on the next page. So these are ideal sources. These are practical or real life sources. In real life sources, we need to take resistances into account. So if you have 2 real life sources connected in series, you would simply add up the resistances of that source in series. And so the total Thevenin resistance would simply be the 2 resistances added together. That's all. So if you have 2 batteries in series, and if each battery has 300 milliohms or 0.3 ohms of resistance, you'd simply add them up, 0.6 ohms. So if you wish to perform an experiment, take 4 batteries together and see if you can measure the resistance of these 4 batteries connected in series. Because that would give us sufficient resistance. Okay. So RTH for series connection is simply summing up all the resistances in series, and then VTH, the Thevenin voltage, is simply summing up all the voltage sources in series. So straightforward as far as equations or analysis goes. All right, how about voltage sources connected in parallel? That's not a permitted combination. In real life, it could cause fires. The reason is electrical current always flows from a higher potential to lower potential. So if you connect 2 batteries together with dissimilar voltages, you could take a battery with like 3 volts, another battery with 1.5 volts, connect them parallel, meaning positive of both batteries are connected together, negative of both batteries are connected together. Well, because the 1.5 volt battery is at a lower potential, current will start flowing from the larger one to the smaller one. Now, if we stop the reaction after a certain point, perhaps nothing happens, but more likely it would result in a lot of thermal energy being expended and thus result in perhaps explosions or sparks or fires. And so it is not permitted. It violates KVL, right? Would not work. If you have a loop with 1.5 volt and you have a same loop also has a voltage of 3 volts, some of the voltages does not add up to 0. And so that would not work. However, if you have a real life power source which has some resistance, we still would not want to have two dissimilar voltages connected together unless we have like significant resistance in the line. But let's say we do have a connection like this. Well, in order to find the RTH, we would consider that R1 is in parallel with R2. Okay, we would consider R1 is in parallel with R2, and that gives us our Thevenin resistance. And then VTH is a little tricky. Okay, VTH is tricky. This is derived from superposition and voltage division. Okay, we'll see that later on. So VTH is what fraction of V1 appears at the output terminals. Okay, so these are the terminals of analysis. My VTH and my RTH are measured here. VTH is a sum of what fraction of V1 appears at the output. So it's this fraction, and of V2, it's this one. Okay. So weighted sum of the value of the resistors. Yes. Oh, you mean ideal voltage sources. So if we have two voltage sources, one with 1.5 and the other one with 3 volts, as an example, law of conservation of energy is not satisfied. So simply stated, KVL would be violated. But in practical terms, if you have two dissimilar batteries connected together, current will start flowing from the higher potential to the lower one. And so there is a potential to, lot of thermal energy being expended and could cause a short circuit, could start a fire. Yes. Why are we using the second resistor for the first voltage source? We will prove that mathematically in just a few slides. Okay. All right. How about current sources? What is the property of a current source? Property of a current source is to supply its rated current between its terminals, meaning anything that's connected in series with a current source will receive that current, right? So if you have parallel connections of current sources, yes, we can do so. Series connections, no. Because two dissimilar currents cannot exist in the same series branch. It's just not possible. So if you have I1 and I2, which have two dissimilar values, then we cannot use them in series. Okay, and while it's KCL. However, if they have, if we have them connected in parallel, then yes, we can use it simply by taking these two terminals simply by taking the parallel sum of I1 and I2, and then Norton resistance or the Thevenin resistance in this case could turn out to be R1 plus R2. And again, the Norton current is also a weighted sum. Okay. All right. So if you have parallel connected ideal sources, you apply KCL at the top, you have I1 coming in, I2 coming in, and then I1 plus I2 going out. And so the total Norton equivalent is simply a sum of those two parallel connected currents. So in general, Norton current for current sources is simply the sum of the two. Similar to the example of the voltage sources where we apply KVL to determine the total output, we can apply KCL to determine the total output for this. So here you have one current source going up, one current source going down. So if you take a look at our circuit, which way is the total current flowing? If I have IN, which direction is IN flowing? Is it going up or is it going down? Down, yes. The numbers 5 and 7, so it's down, and the value is 2 milliamps. Okay, 2 milliamps. And if you connect them in parallel, Norton current is I1 plus I2, total sum, and the Norton resistance is R1 parallel R2. Okay. All right, so first strategy to finding Thevenin or Norton equivalent circuits. Let's say we have a simple connection of sources, two voltage sources, V1 and V2, each with a source resistance of R1 and R2. And what we can do is we can perform source transformation. Now, source transformation, as I said, is a little tricky. The way it works is like this. You'd have to take you take out the voltage source with a resistor in series. You note down the nodes where it was connected. Okay. In this case, it's connected at these two nodes. And because it's connected at those two nodes, once we transform this, we have to plug it back into those two nodes. So AB, AB, this can be transformed into a current source. This is A, and this is B. Resistance remains the same. Norton current is determined by applying Ohm's law. Let's take a pause. Let me know if you have any questions. Which one? This here? Here? That's source transformation. I'm going from Thevenin, like a voltage source, to a current source. So source transformation. Source transformation. So if one is transformed, I1 and R2, we can do the same for I2 and R2. And the terminals will remain the same between A and B. So between A and B, and now I have two current sources and two resistors. All are in parallel. Thus I can reduce them. Sum of the current sources to get me IN, and sum of the resistances to give me Rn. Once I have that, I can transform back. So both of these okay. Both of these are accomplished by applying source transformation. And this is only possible in certain cases. A question was asked earlier about the derivation of the equation. It's not on this slide, but I can explain right here. Right? I1 is obtained from Ohm's law, V1 over R1. I2 is obtained from Ohm's law, V2 over R2. If you sum them up, you get IN is equal to V1 over R1 plus V2 over R2, right? And then Rn is the parallel combination of R1 and R2. And so we have that. This should be 2, R2. And then we need to find INRN. That means it's these two terms multiplied, which results in this. Okay. Again, let's take a pause. Let me know if you have any questions. Yeah. Yeah. The parallel combination of R1 and R2. That's all. Yeah. Okay. All right. So that was one method. Second one is to determine the open circuit voltage and the short circuit current between those terminals. These are the techniques that I typically teach in circuit analysis classes. By far, the most popular and the most convenient. Okay. So what we do is, if we have a large circuit and we need to find the Thevenin voltage between its terminals, all we do is we perform the analysis, keep the terminals open, and we try to calculate the voltage at that open circuit. That open circuit voltage, VOC, is the Thevenin voltage for that particular network, for that particular circuit. Okay. And then for short circuit current, Norton current, we short out these two terminals. If we chose plus and minus on the left, we need to keep the same polarity. So short circuit current would actually flow down. So it's flowing down. Right? You calculate the current that's flowing down in that wire or in that short circuit. And that short circuit current is the Norton current. Okay. Don't look at the examples yet. No need to do that yet. Just understand the concept. You have a large circuit and you're trying to determine the Thevenin equivalent network between any two pairs of terminals. In case of the voltage sources, we simply the outer terminals of those batteries, right? But regardless of the fact, it is a linear circuit and you have only two terminals at the output. So you're trying to measure the Thevenin voltage, the Norton current, and the Thevenin resistance, all from those two terminals. And to do that, you apply a variety of techniques. So Thevenin voltage is simply, this is how easy it is in a meter. Let me use a real life example of using a circuit, right? How many of you are done with the lab this week? Okay. Not yet, right? So let's say you're in the lab, you're trying to measure. Let's say you're at this lab bench and you're trying to measure, you have a circuit built up, 1 voltage source, 5 resistors maybe, all right? And then you have a pair of output terminals. Pair of output terminals, you want to find the Thevenin voltage, the Thevenin resistance, and the Norton current between those two pairs of terminals. It takes less than 2 minutes, not even that, less than 1 minute actually to get everything done. Because Thevenin voltage, as you see here, what does it say? Open circuit voltage, right? Open circuit voltage. I used to, just on a side note, I used to love walking around in the class before I use these tablets. Now I'm like fixed, so I'm getting antsy. Like I like to move around. Anyway, so open circuit voltage. How do we measure voltage? If you have a multimeter, you have two terminals. How do you measure voltage? You haven't done that yet in the labs? Just connect it there. That's it. That's all it is. You turn the multimeter on, power up your circuit, take the two pairs of terminals, connect it across those pair of terminals where you want to find the Thevenin voltage. That measured voltage at those open terminals, which is the open circuit voltage, is your Thevenin voltage. That's all it is. Now, if you wish to measure Norton current, what do you do? Or let's say if you wish to measure current with the multimeter, what do? You put the meter in current measurement mode, and you would insert the meter in the middle of the circuit where you want to measure the current, right? Well, here our terminals are right there. Those terminals are open. We haven't placed a short circuit yet. But if we take a multimeter and put the meter in current measurement mode, it behaves like a short circuit. Resistance is very low. So again, you don't have to do anything. Keep that meter connected on those pair of terminals. Switch from voltmeter to current meter or ammeter and measure the current. That's it. Done. So it doesn't take more than a minute to take those two measurements. Well, on the meter, you still have to switch out the terminals physically because voltage and current measurement are different terminals. But the actual measurement, nothing. Doesn't take long. Now, for Thevenin resistance, it's a little different. And we'll talk about that later on. But does everybody understand this? Open circuit voltage and short circuit current. Okay, you take any circuit and you wish to measure the Thevenin voltage, then you simply take those multimeters connected to output terminals. That's your measurement. So theoretical analysis is actually going to take longer because in theoretical analysis, we want to calculate what that voltage would be between those pair of terminals. We keep it open and we measure it. For Norton current, we have to short the terminals. Because current needs a pathway to flow, So when you place a short, the current runs that short circuit. So it's known as short circuit current, ISC, and that current is the Norton current. Okay. And then finally, the easiest way to find Thevenin resistance, apply Ohm's law, which I do not recommend to students at all. Okay. So the simple reason being, we have three unknown quantities: VTH, Thevenin voltage, Norton current, and Thevenin resistance. Okay. If you use two of these quantities to find the third, we need to be absolutely certain that those first two quantities are correct in value, right? Because if one of these two quantities is incorrect, then your third one is also incorrect. Does that make sense? And so we want to have the skill and the knowledge to be able to find all three quantities independently, and then we can verify our answers. All right, this is an important topic, so please review this as soon as you can. If you have time right after this class, review it, and then have your questions ready, and we'll pick up here again on Friday. Okay.